Hey AP, in this video we're going to talk about structure and strength of acids and bases. So we've talked about strength of acids and bases when we looked at strong versus weak acids and bases, and we said that our strong acids and bases are going to completely dissociate, break apart into their ions, which means it's a one direction reaction, whereas weak acids and bases do not completely dissociate into their ions. Therefore, they sit at an equilibrium and we have that double arrow. But within weak acids and bases and within strong acids and bases, we can also begin to determine which of those is slightly stronger or weaker than the others. This is based off of a few influences of strength. So strength can be looked at looking at strength of bonds. So strong bonds would be reluctant to break. And if they're very strong bonds and they don't want to break, well, that means they're not going to break into its ions, even in solution. If they don't break, they can't make an acidic solution because we're not going to dissociate. If we don't dissociate for an acid, that means that we don't have a hydrogen ion in solution. No hydrogen ions, no acid. The other thing we have to look at is polarity of bonds. If a bond has a high polarity, that tends to increase the acidity of the hydrogen. And that means that it tends to increase the ability of the hydrogen ion to dissociate or break off from our acid. We find that acids that are very soluble in water will dissociate completely. And this makes sense because water is a polar substance. And we know that like dissolves like. So strong bonds reluctant to make even solution. This makes for a weak acid or base. So if I was looking at a generic acid, HA, right, this is my anion and my acidic hydrogen, and it was in water, we would see that our negative part of our water is going to attract our positive part of our acid. And so this interaction happens, hydrogen bonding here, and we are going to then pull our hydrogen off of our acid. And the more polar this bond is, the more easily it is for this hydrogen to get pulled off, dissociate, and then become a hydrogen ion in solution. And that's why sometimes we see things written because this hydrogen then attacks or is attached to the water. So we might see H3O plus because that's one oxygen and three hydrogens. Or some people might say, well, this broke off, is dissolved in solution. So they might just say, well, we have hydrogen ions floating around in solution. So you might see either one written. Just know that they're both referring to how acidic or the hydrogen ion concentration of our solution. Another thing to note that we talked about a couple of times is the smaller the pKa, the stronger the acid. And this follows the same route as pH as well, right? Smaller pHs means stronger acids or more concentrated acids. We have higher hydrogen ion concentrations, and pKa's follow the same structure. Let's look at a few different types of acids and then compare them to see what's a stronger versus weaker acid. And then bases follow similar patterns as well. So if we have a binary acid, so a hydrogen with another anion, so some other anion, which we'll call X. The more electronegative X is, the more acidic. And remember, our most electronegative elements on our periodic table, remember, fluorine is the most electronegative element, okay, here. And so nitrogen, oxygen, and fluorine tend to be some of our top three electronegative elements. They're small, they have lots of electrons around them, they want to gain more electrons, so they're very electronegative. The longer the bond length, the more acidic. That makes sense. If the bonds are longer, right, we know that a single bond is weaker or is weakest, right, and a triple bond is our strongest. So single bonds, very long compared to triple bonds, short. Longer the bond length, the weaker it is, the more acidic, so the more easy it is for that hydrogen ion to pop off. So if I was looking at NH3, which is ammonia, versus CH4, which is methane, I would want to see what is more acidic. I would look at two things. I would look at the electronegativity of my element attached to my hydrogen, and the bond length. We can see that all of these are single bonds, so bond length is relatively the same. They're also within the same row of the periodic table. So between carbon and nitrogen and hydrogen, there's not much difference in the size of these two atoms, so bond length is about the same. So then I would next go to my polarity. Well, between nitrogen and carbon, nitrogen is a more polar, or not polar, is a more electronegative element than carbon. So this bond here is a more polar bond. And if this is a more polar bond, that means it's easier for these hydrogens to get knocked off. We also notice that this also helps us exhibit hydrogen bonding. This is just a more polar molecule in general. So because of this stronger polarity in this bond, NH3 is going to act like a stronger acid than CH4. Notice that neither one is classically an acid, but they can have acid tendencies by losing those hydrogens. What if we have two known acids, HF and HCl? Well, we know that HCl is a strong acid, and we know that HF is a weak acid, but that might come as a surprise to you because of, if we start by looking at polarity, well, polarity, fluorine is the most electronegative element. So this is one of the most polar bonds we can have. But remember that first we looked at bond length. And the bond length, or the strength of the bond, how long it is, that's going to have a bigger influence on the ability of the hydrogen to pop off than electronegativity. So for our rank of influences, the top influence is the length of bond. Okay, so our top influence is the length of bond, followed by the polarity of the bond. So if we're looking here, yes, fluorine is a much more polar element or much more electronegative element than chlorine. However, if we look at where they are on the periodic table, fluorine is a lot smaller than chlorine. It has one less shell. So because it's smaller, it's able to get closer to that hydrogen and hold on to the hydrogen a little bit better. And by doing that, it means it's harder for the hydrogen to dissociate or break off. And so it's a weaker acid. So the one that's more acidic is HCl, and that's because of the bond length is greater. So it's easier to lose our hydrogen ion. What about if I have a hydrogen attached to an element and then that's attached to some oxygens? Well, in this case, we're going to look at the inductive effect, which in the inductive effect, this is where we can have attraction of electrons away from our hydrogen atom. So because of the electronegativity, the oxygen influences electronegativity of this element, and then we're going to pull all of our electrons towards the oxygen, and then the hydrogens are going to pop off. So the more oxygens that we have around this hydrogen, around this element here, the more of an inductive effect we're going to get, and therefore the easier it is to lose this hydrogen. So the more oxygens around the central atom, the more acidic. So if I'm looking at this is nitrous acid versus nitric acid. Well, in nitrous acid, I have two oxygens that are able to pull my electrons away. But here in nitric acid, I've got three. So I've got a much stronger pull of electronegativity of pulling my electrons over here away from my hydrogen. So because I'm able to pull and keep these electrons away, my hydrogen is much more easily able to dissociate and pop off and just be an ion in solution. So we have more oxygens and the inductive effect. So my third influence on my ability for my hydrogen to pop off, or my influences on strength of my acid, is my number of oxygens. We can also look at chains of carbon. So this is shown as RCOOH, and COOH makes a carbon double bond OH. It's a type of functional group. If you take organic next year, or if you're in it this year, you'll learn about functional groups and what those are. We don't care about that now. We just know that this is a thing. And then the R stands for the rest of the compound that doesn't have the acidic hydrogen or the functional group. Is just the carbon chain that comes over to the side of it. So we found that, or scientists found that the shorter the chain of carbons, the more acidic it's going to be. So the more easily it is to pop off this hydrogen. So if I'm looking here between CH3, CH2, COOH, so this is a CH3 group, which we have here, a CH2 group, which we have C2H's. These would be hydrogens coming off. I just didn't draw them, so my paper didn't look so messy. So 2 carbons here, so CH2, and then COOH. So it looks like that. So I'm comparing this molecule to my next one, CH3, so CH3, COOH. Well, here the carbon chain is just 1 carbon versus 2 carbons, and we said the shorter the carbon chain, the more acidic. So this guy is going to be more acidic than this one. Well, what if I start changing out my hydrogens for something like chlorine? Well, that means that I'm going to have something that's more electronegative in my compound. If I'm adding in something that's more electronegative in my compound, that's going to influence the strength of my acid because now I'm having a greater inductive effect. So here I have CClH2, so carbon, a chlorine, and 2 hydrogens to a carbon double bond OH versus a carbon attached to 3 chlorines, carbon double bond OH. Well, here, this is able to, because they're still electronegative, not only is it a short carbon chain, but high electronegativity in these chlorines, therefore more polarity. So that's going to pull my electrons or attract them over here, which means my hydrogen is much more easy to pop off. So again, even though they're not just carbons and hydrogens, now I'm adding in electronegative elements, still follows the same rule. So again, the inductive effect, which is the reason that all of this happens, is a highly electronegative atom can affect a bond's polarity 2 to 3 bonds away. So it has greater influence the more electronegative it is. It can reach further. Its attraction reaches further. So in the above, looking at the difference between just a CH3 versus a CCl3, my chlorine atoms attract the electrons from the COO and increase our acidity because it continues to pull or attract those electrons. If I were to go another step and replace my chlorine atoms with fluorine atoms, well, because they're over here, right, they're not directly attached to my hydrogen, fluorine is more electronegative. They're going to continue to attract our electrons even closer, and it's going to further increase the acidity because the fluorine is even more electronegative. Another thing to note is that while we look at the strength of acids and bases, the stronger the acid or the base, the weaker its conjugate is going to be because it's easy for that one to break apart and lose what it's supposed to lose or gain what it's supposed to gain. It's going to be harder then for the reverse to happen. So just a note, the stronger the acid, the weaker its conjugate base, and then vice versa. The stronger the base, the weaker its conjugate acid, weaker, stronger, and so on. So we'll continue to practice that and look at some different examples as to how structure can influence the strength of acids and bases.